Okay, so it's my pleasure to introduce Heejoung Kim from Ohio State University, and she's going to talk about the n-periodic homeomorphisms and volumes of mapping tori.
Yeah, thank you for having me today, and thank Funda for allowing me to speak here. So today I'd like to talk about big mapping class groups, in particular, and periodic homeomorphisms and volumes of mapping tori, which is a joint work with Elizabeth Spield, Chris Leininger, and Marissa Loving. So here is the outline of today's talk. First, we discuss finite type surfaces and mapping class groups, and mapping tori of homeomorphisms of finite type surfaces. And then we consider infinite type surfaces and particular homeomorphisms there, like namely and periodic homeomorphisms. And lastly, we will discuss our result on mapping tori of homeomorphism of infinite type surfaces. So let's consider finite type surface first. So in this talk, suppose a surface S is a connected orientable surface without boundary with negative order characteristic. Then a finite type surface means that a surface is homeomorphic to a complex surface and at most finite many points remote. Or algebraically, the fundamental group of the surface is finite degenerate. And if a surface is not of finite type, then the surface is of infinite type, and in this case, the fundamental group is infinitely degenerate. So here's some finite type surfaces. So genus 2 surface, genus 2 surface with 2 punctures, and genus 1 with 2 boundary components. And it is known that the homeomorphism type of finite type surface is determined by the triple, the genus, the number of punctures, and the number of boundary components of the surface. And here are some examples of infinite type surfaces. So the first one is the Neso monster surface, which is the infinite genus surface with exact one end. And the next one is Jacob's ladder surface, and it is the infinite genus surface with 2 ends. And the third one is the blooming counter tree surface, which has infinite genus, and the space of ends is a contour space. And the last one, the contour tree surface, is the planar surface, meaning not accumulated by genus, and whose space of ends is a contour space. Sorry. And these pictures are from Aromariona Bremi survey paper on mapping class groups of infinite type surfaces. And the paper is a great reference for big mapping class groups. And there is a topological classification of infinite type surfaces by using genus and boundary components, and additionally the topology of the space of ends. Okay, so now for a connected oriented surface, the mapping class group is a group of isotopic classes of homeomorphism of S. So for example, for a genus 2 surface with 2 punctures, say P and Q, then the homeomorphism permitting 2 punctures P and Q is an order 2 element of the mapping class group. And one important element of mapping class group is called a then twist. So a then twist is obtained by cutting the surface along a simple closed curve, for example here alpha, and then twisting one side by 2 pi, like 180 degree, and then regluing. So let's look at it. Then to see what the then twist about alpha really does on the surface, we can see another curve, say this red curve. Then the image of the red curve under the then twist about alpha is that a curve turns around when it meets alpha, and then follow alpha like that, and then follow the original curve. And locally, the then twist looks like this. So a then twist has infinite order, and a mapping class group is finite generated by such then twist. And note that a mapping class group is not hyperbolic because it contains Z2 as a subgroup. So for example, for two distinct curves, the then twists are commuting. So mapping class group is not a hyperbolic group. Okay, and then for a finite type surface, there is the Nielsen-Thurston classification of elements of the mapping class groups. So here is the theorem. So given a homeomorphism, at least one of the following holds. So F is either periodic, meaning some power of F is isotopic to the identity, or F is reducible, which means F preserves some finite union of disjoint simple closed curve. And the last case, F is pseudo-Anosov, meaning no power of F fixes any simple closed curve. So in other words, F is neither periodic nor reducible. We also called a homeomorphism F as a pseudo-Anosov element if there exists a pair of contracting, expanding, transverse measured foliations on the surface, which preserved by F. So the most interesting case is the last one. And pseudo-Anosov mapping class groups are genetic in some sense. So here's some examples of each type. So homeomorphism permuting punctures have finite order, so they're periodic. And the then twist about a curve is reducible because it preserves the curve we use for the then twist. And there is a Thurston's construction of pseudo-Anosov elements. So for two curves, if alpha and beta have minimal intersection and the complement of the union of two curves is the union of topological disks, then the product of the then twist becomes pseudo-Anosov. So and now I'd like to briefly mention a hyperbolic space called a curve graph, where a mapping class group acts by isometries. So curve graphs are one of the important tools to study mapping class groups. So here's the definition. So the curve graph of a surface is a graph whose vertices are isotopic classes of simple closed curves. And we put an edge between two vertices if they have representative curves which do not intersect. Then for a finite type surface, the curve graph is locally infinite since for a simple closed curve, there are there are infinite many curves. They do not intersect with that curve. And the graph is actually hyperbolic space. And we understand hyperbolic geometry well. And the action of the mapping class group on the curve graph is actually acylindrical. So, and group elements can be characterized as the group action on the curve graph. For example, an element is pseudo-Anosov if and only if F acts lexodromically on the curve graph. Also, there are other spaces where a mapping class group acts, like mapping class group acts on the triangular space, properly discontinuously, and the arc graph, and there are Pence graphs. So let's move on. Now I want to say some properties of mapping class group. So now we are consider a mapping class group of a finite type surface. So first of all, mapping class group is finite presented. And mapping class group is automatic, meaning it is equipped with several finite state automaton. For example, we can tell if a given word representation of a group element is in a canonical form. And we can also tell if two elements are given in canonical words differ by a generator. So algorithmically, mapping class groups are great. And for example, mapping class group has a solvable word problem, meaning there is an algorithm that decides whether or not a group element is equal to the identity element. And MapS is a residually finite group, meaning the intersection of all its subgroups of finite index is trivial. And mapping class group are related to other interesting groups, such as braid groups and outer automorphism groups. So the mapping class groups is of importance in many areas, like for example, like type-cumulative space and modular space of spaces. And mapping class groups are a very important topic in geometrical theory. And usually we use mapping class groups to test some conjectures and techniques. So now let's move on to mapping torus. So now, so for a homeomorphism F, we can construct a 3 manifold, which is obtained from the surface across an interval by gluing the bottom and the top using the homeomorphism of S. So in other words, the mapping class group, mapping torus is a fiber bundle whose base is a circle and whose fiber is the original manifold S. And for a finite type surface S, a mapping torus has a hyperbolic structure if and only if the homeomorphism is pseudo-Anosov. So if the mapping torus has a hyperbolic structure, then MF is a complete Riemannian manifold with constant sectional curvature -1. So we can talk about the volume of MF. And then in fact, the volume of hyperbolic manifold is a topological invariant. So let's see. So we defined a mapping torus. Then one might ask that for a finite type surface and pseudo-Anosov element F, whether we can estimate the volume of the mapping torus. So in fact, Brock proved that we can estimate the volume in terms of length of F in the Weil-Petersen metric on the type-cumulative space. So there exists a constant K such that the volume is bounded below by 1/k times the length of F and bounded above by K times the length of F. So for the proof, he used the pantograph of S, which is a coarse model of the type-cumulative space with the Weil-Petersen metric. So let's look at the pantograph. So like specifically, the pantograph is a graph whose vertices are now pant decompositions of S. And we put an edge between two pant decompositions if they differ by an elementary move, like a particular pant move. So here are the pictures for elementary moves. So for a 4-punctured sphere from this pant decomposition to here, or vice versa, we call this move as NS move. Like N stands for like sphere. And for 1 punctured torus from this pant decomposition to here, or vice versa, this elementary move is called it like NT move. Like T stands for torus. So if if we have like elementary move between two pens decompositions, then there is an edge. And it turns out that for a finite type surface, the pens graph is connected. So Brock used this pens graph to find the bounds of volume of the mapping torus. And in fact, Agol refined Brock's upper bound as follows. So since the pens graph is connected, so for given a pens graph, say P, we have a path from a pens decomposition P to FP. Then the theorem says the volume of the mapping torus is less than or equal to the volume of the regular ideal octahedron times the number of NT moves on that path plus 2 times the number of NS moves in the path. Okay, let's move on. Then here's the idea of the proof. So given a pens decomposition P, so we have a path from like P to FP, and in the surface cross-on interval, like the mapping torus, we insert the pens decomposition on S times I over N for each I. And then we consider a curve on PI plus 1, where elementary move happens from PI. Okay, and then we drill out such curves. So we drill out such curves from the mapping torus. Then we consider the link complement MC, which is the complement of the neighborhood of BI in the mapping torus. Like BI is the curve, and then we just think about the complement of the neighborhood of those curves. Then it turns out that the mapping torus MF is obtained from MC by then filling on the boundary components corresponding to the link. Okay, then by Thurston, actually the volume decreases under hyperbolic then filling. So we have the first inequality, and Agol computed the volume of this model manifold MC as the regular ideal octahedron times NT plus 2NS. So it means if there is NT move between PI and the next pens decomposition PI plus 1, that meaning there is a like elementary move in a punctured torus, then the volume of one octahedron contributes to the volume MC. And for NS move, namely elementary move between a 4-punctured sphere, then the volume of 2 octahedrons contributes to the volume of MC. Okay, so any questions so far? I mean, that's about like finite type surfaces.
Could I ask a question about this PS, because you said it's connected? But are there any? Is anything known about the genus of the graph viewed as like a one-dimensional related to the surface?
So as far as I know, like the pens graph is connected and like simply connected as well. But
okay.
Yeah, for finite type surfaces. Yeah.
Thank you.
Yeah. So now,
Heejoung, so on this surface, so I'm trying to understand how this. So what do you exactly glue?
Like on mapping torus or?
Yeah. So you say, given a pens decomposition, you have this the path, and yeah. So inside the taken surface.
Uh-huh.
So what is done there? What is glued to what?
Yeah. So basically we are thinking mapping torus. So like we insert pants decomposition and then we just re-gluing. Like we think about the surface times interval. And then because basically we are thinking like mapping torus, so we just glue the top and the bottom by using the homeomorphism.
Yeah, okay, but before that, you look at the pants. There's an ice-pants decomposition in it. So
Yeah.
Okay. All right, thank you.
Yep. So now let's see. Now let's move on to infinite type surfaces. So, but we can still define the mapping class groups. And let's see some examples. So, an obvious example, an obvious element is a homeomorphism which is compactly supported, meaning the homeomorphism is the identity outside of a compact subset. And an important element is a handle shift, which is introduced by Patel and Bremis. So let's see the construction. So let lambda be the surface obtained from R times unclosed interval like 1 to 0. And then by removing disks of radius 1/4 centered at like t comma 1/2, like for integer t. And then we attaching torus with one boundary components of each such a disk. So something like this. Then let H be a homeomorphism of lambda that shifts the handle at like t comma 1/2 to the handle at t plus 1 comma 1/2 and is identity on the boundaries. So this is the picture. So this lead curve goes to this curve when we apply a handle shift homeomorphisms. So just shift the hands. Then actually we can embed this one into any surface with at least one end accumulate by genus and extend H by the identity to the homeomorphism. So I have more picture. So for example, a finite number of handle strips embedded in a ladder surface, meaning an infinite type surfaces with exact two ends like that. And two ends are accumulated by genus. Then the product of pairwise commuting handle shifts is a homeomorphism. So for example, we have like two handle strips in this picture, and the product of commuting handle shifts become a homeomorphism. For example, like shift this one like that, and then like for this strip, we think about this handle shift, then the product is actually becomes a homeomorphism as well. So, and note that Patel and Bremis showed that like handle shifts and then twists topologically generate the pure mapping class group of an infinite type surface. So here the pure mapping class group means a subgroup of mapping class group just consisting of elements that fixes the ends. Okay. And now, so for an infinite type surface S, we usually called a mapping class group as a big mapping class group. So here's some reasons. So for example, map S is infinitely generated. And if a set S generates map S as a group, then the set cannot be compact. And map S is not locally compact, and map S is homeomorphic to the Berry space. So this is very big. And MS is not acylindrically hyperbolic. So previously a finite type surface, the mapping class group acts on the curve graph acylindrically, but there is no hyperbolic space where a big mapping class group acts nicely. So let's move on. So now we restrict ourselves to an infinite type surface without planar genus, planar ends, and with n ends accumulated by genus. So we are thinking surface like accumulated by genus. Then there is a end periodic homeomorphism, which is a shift by one in the ends. And here is the precise definition. So there exists M such that for each end of S, there exists a neighborhood of UE of E, so that either F to the M of UE is contained in UE, so that like shifted by one. And the set F to the MN UE form a neighborhood base of E. Or the negative power, like F to the minus M of UE, is contained in UE, and the sets F to the minus MM UE forms a neighborhood base of the end. So the first case, the end is called an attracting end, like because we think about like positive powers. And then the second case is called a repelling end, because we think about like negative powers. So informally, and periodic homeomorphism is a shift by one in the ends. So for such homeomorphism, like and periodic homeomorphism, Handel and Miller outlined an analogs theory to the Nielsen-Thurston classification of homeomorphisms of finite type surfaces. Okay. Yeah. Then so Handel and Miller defined reducible and periodic homeomorphisms and showed that they preserve a pair of contracting and expanding transverse measured geodesic lamination as sto-Anosov elements for finite type surfaces. So let's see the definition. So an end periodic homeomorphism is reducible if F has no periodic curve and no line with one end in the attracting end and the other in the repelling end. So that there exists a like integer k such that F to the k preserves the line. And there is no curve gamma such that F to the M of gamma is contained in like attracting end, but F to the M of gamma is contained in the repelling end. So if these three conditions are satisfied, then the end periodic homeomorphism is reducible. And additionally, Elizabeth Field and Chris Leininger and Marcel Loving and I introduced an additional condition and defined a strongly reducible and periodic homeomorphism. So for a reducible homeomorphism, if there is no periodic lines, then we will say the homeomorphism is strongly reducible and periodic. So we just add one more condition for the line, like periodic line. Okay. Then actually Bentley gave an example of reducible and periodic homeomorphism in his thesis. So for a two-end surface, the product of the twist about three curves like alpha, beta, and gamma. And then the hand shift is reducible and periodic. And actually his proof of irreducible, his proof is relied on like building and analyze the corresponding weighted train tracks. But on the other hand, we also provide a general construction of reducible and strongly reducible and periodic homeomorphisms by using like self-surface projection and curve complex geometry. So specifically for a boundaryless infinite type surface with n ends, and each end like accumulated by genus, that we provide a generalized construction of both reducible and strongly reducible and periodic homeomorphisms. So, for example, let's think about two ends case. Then our example is the composition of the handle shift with a sto-Anosov homeomorphism supporting on a complex subsurface C. And here we will think about like G has large translation length. So say this is our subsurface C, and G is supported by this subsurface C. And like H shifts one genus to the right, like this way. Okay. So for the proof, we will use like subsurface projection and the arc curve graph of C, the subsurface. So for example, to see that F has no periodic curves, so let AC be the arc curve graph of the subsurface C, and let alpha be the boundary of the repelling end, like here, or the boundary of C. And say beta is the boundary of the attracting end, like that. Then to get a contradiction, let's suppose that F has a periodic curve delta. Say we have a delta. Then also remark that delta should be inside the C. Otherwise, by the shift map H, delta cannot be a periodic curve. Like for example, if delta is here, then if we take F, then we just shift one, so it cannot be, so delta cannot be a periodic curve. So this is our setting. So we assume there is a like periodic curve delta. Then let B be the ball of radius 2 about H alpha. So H is the shift map. So H alpha. Then we use inductive argument. So it turns out that the projection of F to the K alpha is contained in B, like the ball of radius 2 about H alpha, and the surface projection of F to the minus K contains in like G inverse B, like G is the sto-Anosov element supported by C. So let's look at the base case. So if K is 1, say, then since F alpha is the same as H alpha, right? Because the support of G is C, so G does do nothing on alpha. Like G is here, something crazy in C, but G doesn't do nothing on alpha. So F alpha is the same as H alpha. So this is in B, right? Sorry. And then now let's think about this one, the second relation. So since H alpha and H inverse alpha does not intersect, right? H alpha maybe here, like shift by 1. And then H inverse alpha maybe here. So they don't intersect. Yeah, so H inverse beta is actually in B. And then now we think about like G inverse. then I mean, like this guy is in G inverse B. Okay, and then by using induction, we can prove this one. Then we assume G has a large translation length. So consequently, for any k, f to the k of alpha and f to the minus k of beta fill the subsurface C. So namely, they have minimal intersection, and the complement is a union of topological disks. Then at the beginning, we said delta is a periodic curve, and actually delta is in C, so delta and alpha are disjoint, and delta and beta are disjoint, and then we also know, since from this one their powers also like disjoint, but this gives us a contradiction because delta is a periodic curve of f. So there's some m such that like f to the m delta is the same as delta. Yeah, but since these guys are below the subsurface C, so it is impossible f to the m is disjoint with f to the alpha and f to the minus beta. So so it gives a contradiction. So it means there is no periodic curve. Okay, any questions on that? Like, does it make sense so far? Like, just read, yeah.
I mean, to me, yes.
Yeah.
You're taking a pseudo-Anosov and with the with a shift, right? So this is some element which is like a pseudo-Anosov on the whole type surface. Okay, thank you.
Thank you. And then now let's move on. So let's consider an infinite type surface of like mapping torus of a like reducible and periodic homeomorphism. So now let's think about mapping torus. Okay, so F is like reducible and periodic homeomorphism, and let MF be the mapping torus of F. Then actually such mapping torus is interesting to consider because for a certain type fluctuation of three hyperbolic manifold, like specifically tot depth 1 fluctuations, any non-compact leaves is a surface of infinite genus with finite many ends. And the leaf is dense in an open submanifold, which is a mapping torus of an end periodic homeomorphism. So the study of homeomorphism of infinite type surface is related to the study of like fluctuated three manifolds, and like mapping torus of an end periodic homeomorphism is still interesting to study. Okay. Then for the right way to discuss volumes of mapping tori of infinite type surfaces, we consider the compactification of mapping tori. So we show that the compactification of the mapping class group, mapping torus, MF, is compact, reducible, atorial, three manifolds with incompressible boundary. And if F is strongly reducible, then MF bar is actually acylinical. So there are a lot of terms, so let me just briefly explain them. So a manifold is reducible means every smoothly embedded two sphere bounds a three ball in the manifold. And M is atorial if for every incompressible torus, the inclusion is homotopy to the boundary. and M is acylinical if no essential annulus exists. Okay. And the last one, M is incompressible boundary, means the boundary is incompressible. So to talk about the volume of the convex core, the compactification, we need to ensure that the compactification admits hyperbolic structure. So for that, we considered like paired three manifold. So here is the definition. So given a three manifold M bar and closed subset, we call it like pairing locus P. We say that like this pair is paired three manifold if the manifold is compact, connected, orientable, reducible, and the boundary of M is non-empty. And the fundamental group of the manifold is not virtually abelian. And the pairing locus consists of like incompressive annuli and tori and contains all tori in the boundary. And any incompressive annulus is properly homotopic into the pairing locus P. And any cyclic, non-cyclic abelian subgroup of the fundamental group is conjugate into the fundamental group of some component of like pairing locus. Then a special case of Thurston geometrization theorem for Heejoung manifolds is following. So for a paired three manifold M bar and the complement of pairing locus, the complement of pairing locus in the boundary is incompressible, then M bar minus the pairing locus admits a convex hyperbolic metric. And if M bar is additionally acylinical and non-degenerated, then there is a unique hyperbolic structure up to isotopy. Then if F is reducible and periodic homomorphism, then the compactification of MF is actually a paired three manifold. And the pairing locus is just empty set. And pairing manifold with incompressible boundary. So the compactification actually admits a hyperbolic metric. So now we can ask the following question. So let's say all MF bar is the infimum of volumes of all such hyperbolic metrics on MF bar. Then the question is whether we can estimate like full MF bar. Okay, that was our question. So then Elizabeth Field, Chris Leininger, Marcel Loving, and I answered the questions as follows. So the infimum of volumes of hyperbolic metrics on MF bar is less than or equal to the volume of a regular octahedron times the asymptotic translation length of F on the Pence graph. So this is our main result. And note that for infinite type surfaces, the Pence graph is not connected, but there is a non-empty subgraph of the Pence graph where each component is invariant by a positive power of F, so that asymptotic translation length is well defined. So we can still think about the length. So here is the idea of the proof. So we define a quotient map H from MF bar, the compactification, to another manifold, say M hat, in terms of decomposition. decomposition of MF bar. And we show that this quotient map is indeed homotopic to a homeomorphism. So then we consider a power of f, like f to the n. And then we drill out a link from that and compute the explicit volume by using Agol's theorem. So we are thinking about like this new manifold, and then by using Agol's algorithm, we compute this like model manifold, like compute the volume of this model manifold. Okay. And here link L is the image of union of finite many circles by an embedding. So just union of circles. So this link complement has like volume as regular octahedron times the number of AT moves, meaning the number of element moves between one punctured torus, plus 2 times the number of NS moves, meaning like the elementary moves between 4 punctured spheres. Then we observe that MF bar to like MF to the M bar minus appends decomposition on the boundary. So this is appends decomposition on the boundary is homeomorphic to a then filling of some of the component of L, the link L, L hat on MF to the M hat. And this manifold is indeed acylitical. So it means there is a unique hyperbolic metric. So like we say like sigma minimum, and this one actually with like total geodesic boundary. Then we have the first inequality by Thurston, because then after them filling the volume is decreased. Yeah, and we computed this manifold explicitly like here. So this is the same as this one. And yeah, let's see this one. And and then we take M such that the translation length of a subgraph omega, like omega of the pentagraph, which is F invariant, is bigger than NT plus 2NS. So we will have this, equality or inequality. And then finally, the infimum of the volume is the same as vol MF to the M bar over N. Okay, but then let's see. Oh, I'm confused. Okay, and then Storm showed that the volume of paired manifold decrease after forgetting the pairing locus. So we have this inequality by Storm. So we have so from here we will use this one here. So we forget the pairing locus, then the volume is increasing, and then so from this inequality we use the here, and then we just this is like just what any questions? My explanation is not that clear, but any questions on that? Okay, so we construct a model manifold, and then we compute the volume for the model manifold very explicitly by using Penn's graph, And then we use like then filling for this inequality and use like paired 3 manifold for this inequality. So we were able to find the upper bound. Okay, let's move on. In fact, our irreducible and periodic homeomorphism examples show that the upper bounds are sharp in the following sense. So there exists a sequence of strongly irreducible and periodic homeomorphism, so that if the volumes are increasing and the ratio converges to the volume of the regular octahedron when k goes to infinity. So yeah. In other words, this one is uniformly bounded, like the difference is uniformly bounded. So our example was like we take handle shift and then compose with Gn. Gn is the Anosov element supported by a subsurface, say C. Okay, then here's some like future directions. So we found a upper bound. So the natural question is, what about a lower bound? And another question might be like, what are algebraic aspects of like strongly irreducible and periodic like homeomorphism? Like what about homology or homology, or some finite property like finite presented, or like something like that. So big mapping class groups are like relatively new, so very little is known. So my result, like this result is very topological result and geometric result, but personally I'm interested in like group theoretic aspects on big mapping class groups. So let me say more about that. Here's some open questions on big mapping class groups. So for example, we can study like relationship with other groups. So for example, like, but it is known that mapping class group is isomorphic to the outer automorphism groups of the fundamental group. But other than that, nothing is known. So that should be interesting. And another direction is explore homomorphisms from big mapping class groups. So for example, mapping class groups of finite type surfaces of genus at least 3 are coffiant. That is, every injective endomorphism is an automorphism, but the analog in the map like infinite type like setting is not known, so it might be interesting. And like find a list of algebraic invariant of map S that determine like the topology of S. Like for example, like Petaline premise prove that the cohomology, the first cohomology characterized the surface S. So this direction is also very interesting to me. Okay, I will stop here. Thank you for your attention. Thank you.
Right, thank you. Thank you so much for the great talk.